Hello everyone, welcome to logicArena. So hope you all are fine. So today we are gonna solve this question, which is implement stack using use, which is obviously a easy question. So let's understand the question first. So we have to implement a stack. What is stack? Stack is a first in. Stack is a last in, first out data structure. That is LIFO data structure using queue. What is queue? Queue is a first in, first out, which is FIFO data structure. I will come into it. First, see this. What are the characteristics or what are the methods we have to create or we have to implement? Okay, so implement with a LIFO data structure, that is stack. Using we can use two stack to implement a we can use two queues. Sorry, we can use two queues to implement a normal stack. And stack should have these properties, which is push, top, pop, and empty. Now, what are these properties? Push int x, that means it pushes x into the top of the stack. Pop, it removes the element on the top of the stack and return that element. Okay. Now, what is top? Return the top element of the stack and boolean empty. If stack is empty, it will return you true. And if stack is not empty, it will return you false. Simple. Okay. Now that are the notes that if you use other language in which language something queue is not defined, then you have to implement queue using list or dequeue. That's the thing. And in queue, you just have to access. You just you can access these properties like you can push to back, you can pop from front. Okay, you can use the size method and you can use the empty method. Got this? Now, what is last in first out data structure? See this. Suppose you have a string Leetcode. Okay. Now, if you push inside stack, if you push it inside a stack, first your L will be pushed, then your E will be pushed, then your U will be pushed, then your E will be pushed, then C, then O, then D, then E. Okay. Now it is last in and first out. What does it mean? Whichever will come or whichever will be pushed last in last, it will be popped first. Last in, first out. Whichever will be last, it will come out first. So if this property holds inside stack, so first we will pop this E. So first we will pop E. Okay. First we will pop E. No problem. Now we can keep track of it. So E now E now we can pop D. Okay. So D now we can pop O. Okay. So now keep track of it O. Now we can pop C. So now keep track of it. Now keep track of it, which is C. Okay. Now you can pop T. Just keep track of it that T is popped out. Okay. Just keep track of it that T is popped out. Okay. Now you can pop E. Okay. Just keep track of it, which is E. Now you pop DC. Keep track of it. So E. Now for L. So keep track of it that you for L. Okay. Now if you match that string with this string, you can see it is the reverse of that string. Okay. So from a stack, we can conclude that property. If you push something, it will give you the reverse string. But in queue, that is not the fact. Whichever will come first, it will be omit first, or it will leave first. Okay. Whichever will come first, it will remove. It will be removed first. Okay. Suppose you are in a cube. So L, then E, then E, then T, then C, then O, then D, then E. So whichever will come first, it will be removed first. So L is the first element which has which is first. So remove L. So first remove L, then E, then DC, then T, then C, then O, then D, and then E. So if you keep track of it, first you have L, then E, then T, then C, then O, then D, then E. So you will get the exact same string of the input string. So that are the last in first out and first in last out. First in first out thing. Last in first out and first in first out thing. Now come to the question. We have to implement this tag using this queue, and you can use at max. We can use at max to queue. So come to that. Suppose first operation, first given operation is push one. Okay. So we can push one. So first given operation is push one. So we can push one inside our queue, and here is a stack for our reference. Here is a stack for our reference that what should be the thing. Do like, am I on the correct path or not? For that, you can keep track of a stack itself. Now push one. So push one. You push one inside the queue and push one inside the stack. Now push 2. So this operation is performed. Now push 2. Push 2. Push 2 inside the queue. Push 2 inside the stack. Okay, this operation also performed. Now push 3. Push 3 inside the queue. Push 3 inside the stack. Got that point? Okay, got that point. So push 3 is now completed. Now push 4. Push 4. So push 4 inside the queue and push 4 inside the stack. Okay. Now pop. What does it mean? Pop. So we have to pop the top element of the stack. But we don't have that stack. It is our reference. It is for our reference. We have that queue with us. So using this queue, we have to implement that stack. So pop. So we need what? 4. We have to pop 4, and we have to return 4, because here it has been given that pop removes the element on the top, pop removes the element on the top of the stack and returns it. Okay, so you have to return it also. Now suppose you want to remove from the queue, but you cannot access the ending element. You can access the front element in a queue. So one plan is that you want that last element. So you can store that elements inside some storage. So use another queue for that. So move one. First move one. Now move two. Move two. Now move three. So whenever my stack, my Q1, if it is my Q1, okay, whenever my Q1 size is equal to 1, I can assure that it is the top element which I can find in a in my stack. So it is my final or it is my top element. So just take it, pop it out and return. Just take it, store it inside some variable so that you can return it after popping from the queue and pop it from the queue. Now you pop it. So 4. Now push 5. Now first, before pushing 5, you have to restore it back. You have to restore the condition. So restore it. So if it is Q2, it is Q2. So you have to restore it. So in Q, you have to access the front element. So first remove that thing and push it inside the queue. Then remove these two and push it inside Q1. This then remove 3 and push it inside the push it inside push it inside Q1. So you have restored that Q1. Okay. Now push 5. Push 5. So just push 5. Push 5. Okay. Now so push 5. So you pop that 4. You pop that 4. Okay. Now push 5 for our reference stack. Push 5 in our reference stack. Now you want the top of the stack. So in our reference stack, what element is our top 5? But in Q1, if we access 5, I have to go through that element. I have to go through that element. So I can do the same thing. First, move 1, then move 2, then move 3. Then my Q1 size is 5, so I can assure that it is my top element. So take it inside a variable and return it. But you have to restore the condition before returning. So how can you restore? If you restore 1, 1 will come after 5, but that is not correct because in the previous situation 1 is before 5, but now 1 is after 5. So it will be wrong. So to overcome that thing, pop that 5 also. Pop that 5 also, and you have a variable something called result. You will store that thing for returning purpose. So pop 5 also. Now restore that thing. So 1, then 2, then 3. Okay. But you have the thing. You need just the top. You need just the top. So you don't have to pop that 5. So just after restoring, you have to push that 5 so that the previous condition will be restored. So that the previous condition will be restored. Now the thing is restored, so you can go through and you get the top element of the stack, which is 5. Okay. So from there we can conclude that thing that when we need to access top first, whenever we need to access the top element of the stack, but it is our reference stack. We have a queue with us. So first move all the elements from Q1 to Q2 until Q1 dot size not equal to 1. Or you can say until Q1 dot size greater than 1. Until Q1 dot size greater than. Until Q1 dot size greater than 1, you have to suppose this. You need 5. So until your Q1 size is greater than 1, like when your Q1 size greater than 1, you have to move. And if your q1 dot size, or if your q1 size is 1, just stop it, because you can now assure that it is the top element of your stack. Okay, so q1 dot size, and then take the top. If have to pop it, just pop it, and again shift all the elements from q2 to q1, so that all elements will be restored. You have to restore the previous condition. So for this restored purpose, you have to restore it. Okay, now come to the code. So we have q1 comma q2 to q. We have, whenever you push something, just push it inside the q1. Okay, you pushed it inside the q1. Whenever you have to pop, so whenever you have to pop, whenever you have to pop, you need the top element of the stack also. Whenever you pop something, you need the top element of the stack. So what you have to do, you have to pop the elements, or you have to move the elements from q1 to q2, and the condition is, while q1 dot size is greater than 1, I have to do that thing. So here is the thing, q1 dot size is greater than 1, until while q1 dot size is greater than 1, just q1 dot front, just push q1 dot front inside q2. Okay, so q2 dot push q1 dot front, just push q1 dot front into the q2, and do that thing q1 dot pop, because you have taken that element, so q1 dot pop. So now when your q1 dot size is equal to 1, you have the top element of the stack. So store it inside a variable called result, store it, and now pop it, because you have to pop that thing. You have to pop that thing from your queue. So pop that element. Okay, so q1 dot pop. Now you have to restore the condition. Now you have to restore the condition. So while q2 dot size not equal to 0, you have to push q2's element inside q1. So q1 dot push q2 dot front. That means you have to push the q2's element inside q1. And whenever you take one element from q2, you just pop that element, so that you can take the next element and push it inside q1. Okay. So that thing is done. The restoring thing is done. Now you have stored the result inside your result variable. So just return that result, that I have popped that element from our queue, or from our stack, because we have to implement the stack and we have to pop the top element of the stack. That's why you are doing that thing. Now top, whenever I have to access the top, the same thing I have previously done in pop. I previously done to implement pop. So result is equal to pop. Pop will give you the top element, but pop will do one thing, pop will eliminate the top element also. But in the top, you don't have to eliminate the top element. That's why. But pop will do that thing, pop will eliminate the top element, but in top we don't have to implement that thing. So we have result, or we have the top element with me. Okay, so after this call you have the top element, but pop will erase the top element, as previously I have said. So just q1 dot push result, that means just push that thing in this situation. Like, you get the 5, but if you restore the condition, 1 will be after 5. That is not the previous situation. That's why I have said that pop that element also, and you have the result with you. So you have restored the thing, just pop that thing then to restore the previous condition. So I am doing this q1 dot push result, and return the result from that, because it is the top element of the stack. And bool empty. If q1 is empty, you can return that stack is also empty. Now come to the time complexity part. Obviously this part is big O of 1, because in this part you are just pushing that thing, you are just pushing the element inside a queue. Pop, this part is q of n, because you have to move because you have the q of big O of n, because you have to move some elements, you have to move n minus 1. If it is total n, you have to move n minus 1 element from q1 to q2, then q2 to q1. So overall complexity will be big O of n. And q dot top, same thing, because you have called that pop function, so also big O of n. Okay. And empty q1 dot empty, you can say that it is also big O of 1 q1 dot size or q1 dot empty condition. We can also say that it is big O of 1. But what is our space complexity? Space complexity, you have taken 2q. You have taken 2q. So q, you have taken 2q. So our space complexity will be big O of 2n. If we said that there are n elements we have to push, so our space complexity will be big O of 2n. Interviewer will not satisfied with that 2. So how can we eliminate that 2? So we have to use it using just one cube. So there is a little bit optimized situation. Suppose first you push one inside your cube. Suppose first you have pushed one inside your cube, and inside your stack you have also, inside your reference stack you have also pushed that thing one. Now you have two inside your queue, and you have pushed two inside your stack also. Okay, but whenever you want to access the top of the stack, you have to move that thing from q1 to q2. I want to just remove that thing. Okay, how to remove that thing? See, you want to remove that thing, so you want to access the two. So why not, if I reverse that thing, if I reverse that thing is possible. I can access, because in queue I am allowed to access the front. So why not take that two? Why not take that two and place it in the front, and then one just reverse that thing. Okay. Now suppose two, one, and you have three. Two, one, and you have three. Okay. So you have three in your reference set. Now you want to the top. You want to access the top. So you want to access the top. How to access the top? 2, 1, 3. You have to move 2, 1 inside another queue. Then you can access the top element. But I want to remove that moving thing. How to remove that moving thing? Now you can reverse that thing. You can reverse that thing. How can you reverse? You have the access of the front element, take it and place it after 2, after 3, sorry, after 3. Take that 2 and place it after 3. Then the next front element will be 1. Take it, place it after 2. Because you are inside a queue now. You are inside a queue. Huh. So take it and place it after 2. Now you have the front. You have the front 3. Okay. And if you pop 3, you the top element will be 2. And if you pop 3 from here, the top element will be 2. So we will apply that thing. Now see the code. So we have the code here. See the code. So here I just take one cube. Okay. So when I first push it inside q1 dot push, I have pushed it in q1. Then after pushing, what I have to do? Just reverse that thing. Now reverse what thing? If you push 3, you have to reverse Like if your stack size is 3, you have to take two elements and pop it and place it after 3. Okay, so do it. If your size is q1 dot size will give you the size q1 dot size, but you don't need q1 dot size number of elements. You need q1 dot size minus one number of elements. You will take that q1 dot size minus one number of elements and place it after the current element, after the current used element. Okay, so size is equal to q1 dot size minus 1. You have to move that thing, you have to move that number of elements. So size minus minus, that means this loop will take care of it, that the loop will run size number of times, and you will push q1 dot from inside the queue, and then you pop the thing. Same thing I have done previously. That means you have 2, you have 1, and you have 3. Okay, now your queue size is 3, so 3 minus 1, you just have to move two elements. You just have to move two elements, and you have the access of the first element. So just take it q1 dot front, just take it, and q1 dot push. Take it and push it inside that queue. Okay, and q1 dot pop it from the first. Now take that element q1 dot front. Now the front element is 1. Take that element and q1 dot push. So push that inside the queue. Take that element and push it inside the queue, and q1 dot pop. So pop that element. Now you have the top element, or you have the reversed element. You have the reversed element. Okay. So this loop will run for big of n time, because you have to move n minus 1 element. You have to move, not move, you have to rotate the thing. You have to rotate the thing, because if I moved, I need another cube, but here I omit that another cube. I move the thing, or I rotate the thing. Okay, now pop whenever you want to pop. You have the top element in the front of the queue, so just result is equal to q dot front. Pop it and return result. And top, obviously your top element is now the front element of the queue, so q1 dot front and empty if q1 is empty. If q is empty, you can say that the stack is empty also. So this operation will take big of one time, and this operation will also take big of one time, big of one time, and this operation will also take big of one time. Got that point? But your time complexity is big of n, but your space complexity is now improved, which is now big of which is now big of n, because you just remove the second q. You only used just one queue. You implement the stack only one queue. That's why your space complexity will be big of n. So all things is clear. Two approaches. I think two approaches. You understand two approaches. I think. Thanks for watching. Do comment. Do consider subscribing. And if you like the video, give a like and comment it.